Scientific notation. All right, so if you have 1.994 times 10 to the negative 23, that's scientific notation. And this first part is called the significand, this part is called the exponent, no, that part's called the exponent, and this is called the base. Okay, so the significand, that's the part before the times 10 to the whatever. Okay, it's called the significand or the mantissa, or some people call it the coefficient, or it's also called the standard factor. Amongst its friends, it's called the standard factor. Everyone else just calls it the significand. Now, the significand is a number, and it has to be between 1 and 10. Okay, so basically, you want to have the decimal point just after the first digit. Okay, so this digit can be a 1, a 2, a 3, 4, 5, 6, 7, 8, or 9. Okay, 10s are out, zeros are out. All right, so this part is called the base, and that's called the exponent, as you well know. Okay, here's some examples. So example number 1, say you have 962.78, and our goal is to write it so that the decimal point is between the 9 and the 6. Okay, now notice that 962 is the same as 96.2 times 10. Like, that's true, right? If you multiply 96.278 times 10, you get 962.78. Okay, so notice this number is becoming smaller, but this number is becoming bigger, both by a factor of 10. Okay, so then notice that we have 9.6278 times 100 is the same as 962.78. We all agree. Okay, now the decimal's in the right place, and 100 is 10 to the power of 2. Okay, so we've now written the 962.78 as 9.6278 times 10 to the power of 2. Okay, this is scientific notation. The trick, though, is that we can say, look, we're moving the decimal point 2 steps to the left. We're going to end up with positive exponents, okay? Because this is a big number. This is bigger than 1, all right, or it's bigger than 9. So it's going to be 9.627 times a big number to make it a big number, to make it into this big number, okay? So I'm moving my decimal points to the left. This number is going to be positive up here, okay? So 2 steps to the left, and that's where that 2 comes from, okay? So you don't have to do these steps. My goal is to get the decimal point between the 7 and the 1, right? So notice that if I can rewrite this number as 0.0714 divided by 10, okay? So if we divide this number by 10, we're gonna we're gonna move the decimal point one more step over here, so we're gonna end up with this number, okay? And dividing by 10 is the same as multiplying by a tenth, and a tenth is 10 to the negative 1, okay? So 0.00714 is the same as 0.0714 times 10 to the negative 1. All right, then, you know, if I could rewrite 0.00714 as 0.0714 divided by 10, I can write it as 0.714 divided by 100. Okay, dividing by 100 is the same as multiplying by 100th, and 100th is 10 to the negative 2. Okay, let's go that one more step. So now we have 7.14 divided by 1,000 is the same as this number. Okay, and dividing by 1,000 is multiplying by 1,000th, so we have 7.14 times 10 to the negative 3. Okay, and this is scientific notation. We have the decimal point between the 7 and the 1. Okay, just where we want it. Okay, but notice we could have also just said, look, here, we're trying to move the decimal place 1, 2, 3 steps to the right. Okay, so 3 steps to the right, negative 3. Okay, isn't that neat? Okay, let's look at example 3. So here's our really tiny number. It's got a whole bunch of zeros, and then 910938. I want the decimal point between the 9 and the 1. The first non-zero digit. Okay, so I'm going to count how many steps there are. There's 1, 2, 3, 4, 5, 6, 7, 28. Okay, so it's 28 steps to the right. And so what I'm going to do is the same thing I did up here. I'm going to write it as 9.10938188 times 10 to the negative 28. Okay, so we don't have to do all these steps. Just count how many places you're moving it to the left or moving it to the right. Okay, remember, this is a really tiny number. Real tiny numbers have negative exponents on the 10. Okay, big numbers have positive exponents. Okay, that's all you have to remember. Okay, example number 4. Here we have 19,837 and 123 thousandths, and we want to get the decimal point right here between the 1 and the 9, so we're going to move it 1, 2, 3, 4 steps to the left, so it's going to have a positive exponent, okay? Because this is a big number, it's bigger than 1, has positive exponents. Okay, small things, less than 1, negative exponents. Okay, so 4 steps to the left, so it's going to be 1.9837123 times 10 to the power of 4. Okay, and that's how to work with scientific notation. All right, let's just look at a quick example. Okay, so if you were asked to calculate the mass of 1 atom of carbon, okay, and this is what carbon looks like. It's often found on a ring or underneath people's chairs. But this is carbon. Diamonds are made of carbon. Carbon nanotubes, very cool and useful if you want to build a space elevator. And here's carbon in the periodic table of elements, and it has an atomic mass of 12.01 grams per mole. Okay, and this is a molecule of Buckminster fullerene. It's carbon. It's just, carbon can often be found in this really neat molecule. And it's a soccer ball, which is pretty neat. Okay, and so the atomic mass of carbon is 12.01 grams per mole, and a mole is Avogadro's number of atoms, which is 6.022 times 10 to the 23 atoms. Okay, so to calculate the mass of a single atom, first we want to look up the atomic mass for carbon from the periodic table of elements. So this number, 12.01, is the mass in grams of 1 mole of carbon. 1 mole of carbon is 6.022 times 10 to the power 23 atoms of carbon. Okay, so 1 mole has a lot of atoms. This relation is then used to convert a carbon atom to grams by this ratio. Okay, so we know that 1 mole has a mass of 12.01 grams. So I'm saying it's 12.01 grams per mole. Okay, and I put the grams on top because my unknown, what I'm trying to find is the mass, right? I'm trying to find the number of grams in 1 atom. Okay, so what this means, the 12.01 grams per 1 mole means 12.01 grams per, now 1 mole means 6.022 times 10 to the power of 23 atoms. So this is the number of atoms, okay? So I'm going to set up a nice ratio. I want to find out how many grams in 1 atom, knowing that it's 12.01 grams in 6.022 times 10 to the 23 atoms. Okay, so I have grams on top, atoms on bottom. Okay, and here's my unknown. All right, x divided by 1 is x, right? So it's my unknown, my mass. So the mass of 1 carbon atom is going to be 12.1 divided by 6.022 times 10 to the 23. Okay, now the easiest way of doing that, don't put this whole number into your calculator, just do the 12.01 divided by the 6.022, okay, which gives us 1.994 divided by 10 to the 23. And dividing by 10 to the 23 is the same as multiplying by 10 to the negative 23, and there you go. Okay, so with doing very little work, we didn't have to crunch this whole number, we just had to crunch the mantisas, right, or the significance, if you will. All right, and there's our answer. And that's it. Have a good day.